I would like to thank the organizers' invitation, and also I'd like to thank for Rujatha's invitation. So I will talk about some works after Coates and Wiles formula. I will not explain too much details. I just explain, all the work I know about that. So, firstly, let me assume that E is an elliptic curve. With Cm. Over Q. Psi E is the corrosion character. And F is the conductor of with Cm over K. E is over Q. Cm is over K. F is a conductor of psi E. Where K is an imaginary quadratic field. Imaginary quadratic field. And this F is the generator of F. It's a generator of F, and then we have the Eisenstein series. H1 ZSL is defined to be this series L, where L is a lattice. This is a lattice in C. Z and S are two variables. Z and S are two variables. And this is equal to this. This is 2S. If Z is in L, then
so this lattice is nothing but you have elliptical over Q, and when you look at it over C,
yeah.
we said that is C modulo.
Yes,
yeah.
yeah.
This is the lattice.
Yeah. So it's EC is isomorphic to C over L. If Z is in L, then we omit in the sum. This sum omit omega equal to minus Z. If Z is not in L, just take all the sum. We define this epsilon n ZL to be H1 Z1L. So John Coates and Wiles, they proved that if n is greater or equal to 3, then this Eisenstein series has some relation with the Weierstrass P function. where PZL is the function. So this is, this is analysis definition by a series. And this one is, what is what? This? N? N is an integer. This, you mean this N or? This? L? L is a lattice. Huh?
No, there is no n on the right hand side, right? You have epsilon n star.
Yeah?
And on the right hand side it is h1 z1 n.
This L is this L?
Right, but n. There is no
Yes, yes. Okay. Maybe I forgot. This N, the definition is where? Here plus N? Okay. Sorry, let's just say.
Yes, just delete that anyway.
Yeah, this is epsilon 1, and when this, we just make this as a definition. Yeah. I'm sorry. Then Zhing and Wiles proved that for n greater or equal to 1, then there is a definition for epsilon 2, but I forgot. I'm sorry. It's here, right? It's here. It's here. It's here. Okay. So then this is n. Okay. Then we have this. Then epsilon n star omega infinity over f. L is in KEF. And we have this formula. This is generator for how to say the. I will explain later. It's F minus N chess KEF over K epsilon star omega infinity over F L. This omega infinity is the minimal positive period. This is the minimal positive period. So this formula is very useful theoretically and computationally. I will explain this, the application of this formula. For example, if we take E to be this, then K is Q, where D is an integer, fourth power pre K is the Gauss field, and then we have the CM, and then we can define I over xy is equal to minus x iy. So we have the f is equal to 1 plus q times d, if d congruent to 1 mod 4, and or 4d, if d congruent to 2 and 3 mod 4. If d, we denote psi d denoted by psi ed. This is ed. This is ed. And then psi 1 is defines on acts on an idea when is an idea in OK is going to be the generator of A, which is congruent to 1 mod 2 plus 2i, and psi d A is psi 1 A times we assume that A is prime idea. And this is the maybe it's d over A, the gender symbol. So this is very explicit. This EF is K adding the F torsion points. I think this formula is clear. So, if we choose m is not 0, and m is not unit in OK, and m is congruent to 1 mod 4, then the conductor K, this over K is equal to MOK. So this means that the KEF is not so big. It's just some power for M. So we can, I don't have explicit data here, but we calculate some, for example, this elliptic curve has Cm over Q minus 7, and this elliptical has Cm over Q11. And it's easy to calculate the conductor. So we want to introduce the admissible sequence. The point is that if we consider the quadratic in this formula, I mean, this is the mysterious part. I mean, this part for quadratic twist of E, if we of this E, this algebraic definition may have some relations. So we are going to define a sequence of quadratic twist. Given we say a sequence pi 1, pi 2, pi n is in OK. They are not a unit. They are not a unit. And given n is distinct prime element. And we assume that pi j is congruent to 1 mod 4. I mean, this is not a, necessary just for convenient. Because if we have this condition, then the conductor is easier. Pi j is prime to f. Then we define m0 is 1, mn is pi 1, pi 2, pi n. Sorry. This is admissible. This is a definition of admissible. This is a definition of admissible. And we denote and assume that J0 is K. Jn is K adjoint with square root of pi 1, pi 2, square root of pi n. This is contained in K adjoint with E Gn. We denote Dn as a set. Is a product of any subset of pi 1, pi 2, pi n. Then the theorem proved by John Coates, Minhong, Zhing, and me and my supervisor Zhao is the following. If K is not Q adjoint with -1, -3, then assume P has a good reduction above 2. V is a place divided 2, and then the V order of the L algebraic means it divided by the Mn. This means traced by Mn 1 is greater or equal to M minus phi E. This phi E is 0, 1. This 0 is 2 divide A1. The 2 doesn't divide A1. A1 is in the Weierstrass equation. For the minimum model. This one is not, this is not important. In the proof, this is not important. The main way to prove this is the following. I just explain the most important thing is the key lemma. To prove this is we have sigma m in Dn let me say Sn is equal to maybe I read here. Sn is equal to the f times Mn. Okay, it's Gn. Okay, it's Gn. Okay, so it's L Gn cosine M1 divided by omega infinity is equal to 2n just Rn over Jn m minus 1 omega infinity over Gn L. So this is, in a lot of papers used this way. So this is really the key to a lot of things. I will explain. It all begins with this formula. Begin with this formula. The importance is that we have, if for any sigma into the Galois group of Rn over Jn, then sigma x on epsilon 1 omega infinity over Gm L is equal to epsilon 1 omega infinity psi E sigma over GM L. So we just, I mean, this growing character, the head character, I just write them the same. So this notation, and we have this, and we have this LSN beside M1 over omega infinity of square root of M is equal to the choice of I over K. Gm minus 1 epsilon 1 omega infinity with the square root of M Gm L. Then if we take the sum of this, if we calculate the sum of the left side, if we want to calculate the sum of the left side, and then we use this formula to calculate it. Use this formula to calculate it for n equal to 1. And n equal to 1, I mean, this is, you have the twist of m. You calculate all the twist of m, in fact. So if you want to calculate the twist of m and compare with, with E and E twist by m, then the only factor you have to calculate is this one. So you take the Galois action on this. I mean, you just time element here. This is common. The important is that this one may go to minus square root of m. So if you take this, if we take a Galois element in this Galois group, so all the square root of, all this element is fixed for any m in Dn. The element is fixed, so you have a factor here. And if you take an element over, how to say that? Let's just say that Jn over K. Then it will move sum of square root of m to minus m. And if you take the sum, they will come to 0. That's the main point. Just carefully calculate the sum. This is the key in Zhao's early papers and also in Yetian's later papers. This way is, I think that's the key. It gives a lot of two factors. And to prove this is relatively easy. You just, you can prove by induction on n. And assume that we proved this formula for n minus 1, then you add one more pi n. Then in this sum, by the induction, m is when n is not equal to mn. Then by induction, the two factors is the order 2 is going to n, and the sum is order 2 is greater or equal than n. So when m equal to mn, it also have this factor. Just use this to make the induction. It's So it's the, of course, we give a lot more, I mean, explain more, but in the paper. But I think this is the most important. All is based on the reduction of this. So what this we need K is not this two field. The choice of K is more than K have to be. The choice of K must be. Let me explain here. Where is K? This K. This K has not many choices. This K is equal to this or this or this or this. For Q equal to 7, 11, 19, 43. This is all the possibility of K. So this is what we did in the paper, and I want to explain my supervisor's result, Zhao's result, because you have L omega in L E1 over omega infinity. This is equal to, this is a BSD conjecture. This is a BSD conjecture. For E over Q times the Tamagawa factor over the torsion, how to say, the torsion point, E over Q, the torsion point. So just write this because this formula holds, then the rank is 0. Yeah. So now, I mean, we can use this way, also the same way. It's in fact the same way to calculate this. I mean, I just explained the idea, not the details. The idea is we can choose some admissible sequence. Choose some, yes? Choose an admissible sequence. Then we can make the order of this is greater or equal. In fact, if we choose the admissible sequence carefully, this is Zhao proved a condition. He wrote it as this is equal to 1. This is a control of this admissible sequence. Then we can set the equal holds to make the order 2 of the left is n. If we choose this carefully, it's easy. I mean, you just check carefully on the reduction to make sure that every time you have only 1, 2 factor, and then you can make this. And this part is relatively hard because if you add one more p, because p can be factored into, for example, into pi 1 times pi 2, and so the growth of n is 2, and in fact in this part, if you goes 2, the 2 factor grows 2. Maybe I should say this is some v or 2, some v. Is a place above 2. Then you have, this growth is, in fact, is 4. Is 4. And this Tabagawa factor, you add one more p, you can prove that in this also grow to 4. So they are, the growth is the same. So the important is that you have to choose those e's such that this is trivial. So Zhao's way is that if you choose at the beginning, E is trivial. The theta subfield group is trivial, and then you can use this way to control the 2 factors of these 2 parts. There are different ways, but I think the difficult is to control this part. This is Zhao's way, and Zhao's method is generalized by Ye Tian, but I don't really understand what Ye Tian did, but I heard from him that, we are very limited on, all Zhao's way is very limited on this condition.
So you have the BSD conjecture, and Zhao's result is somehow saying that you can compute the left-hand side.
No. We don't have the BSD conjecture. All we know that is BSD conjecture holds for P is not 2. Now we know it's right. No, now we don't know. Still the 2, the place of 2 is unknown.
All right, no. So let me try to understand. So we don't know the BSD exact formula for.
Yeah, we just want to prove this. The 2 part of this BSD.
We want to prove it for P equals 2. Okay?
Yeah.
And Zhao's result gives you a way of computing the left-hand side.
Yeah. And the right way is classical.
No, yes, but how do you still compute Sha? The 2 part of Sha? Of course, it's known.
I forgot. In fact, if you choose the admissible sequence, the Sha must be trivial.
Okay. So somehow Zhao's result and something else also helps you to control Sha.
It's not Zhao's way. Zhao have a very strange formula. I forget who found it, but he used that formula. Is easy to calculate.
Yes, Razar, I think. Yeah, there's a paper by Razar. It's an old. Yeah, where he does something about computing 2 part of Sha in explicit, especially for CM elliptic.
Yeah.
So now the whole idea is you have Zhao's result, which helps you compute the left-hand side.
Yeah.
For which you actually knew that's the computational aspect. You really have to use the computer and write a program, right? So
yes.
Give the elliptic curve with complex multiplication, then it will give out the left-hand side, the value of the left-hand side.
I think at that time, Zhao must did the calculations at Cambridge. At the Cambridge.
Yes.
Yeah, he must finish the calculations. Zhao Chunai, my supervisor, he did the calculations. Yeah.
Your supervisor.
My supervisor, yeah, my supervisor.
Zhao?
Yeah, Zhao,
yeah. Zhao, yes.
You met him?
Yeah, I know Zhao. I know this paper, except I've forgotten the details.
Yeah.
But somehow, for you, what I remember from the time that we wrote the paper, what was interesting was you could actually compute that epsilon star n star zn, right? The paper that we wrote, quotes you and I.
Yeah.
Remember we wrote a paper?
It's a very old paper.
Yes. No, you don't need to look at it. I just want to explain to the audience, you're probably a bit lost. So, see, this is probably one of the first lecture where you see the computational aspects coming. Okay? And remember, in everything that we did so far, even on the theoretical side, we were sort of not working with the prime 2. Because the prime 2 is difficult to work with. So we were assuming prime is odd, greater than or equal to 3, sometimes greater than or equal to 5, greater than or equal to 7, and so on. But BSD, on the other hand, when you want to, BSD exact formula, when you want to study it, even the two parts should hold. Right? So now, therefore, you want to check the two parts. The two parts hold on both sides. And so, roughly what Liang is saying is, Zhao's results combined with Liang's program actually helps you compute the left-hand side, the two part of the left-hand side. And the right-hand side, the mystery is Sha. Right? Remember, Sha was still the big mystery. But Sha of 2, again in these cases, when it's an elliptic curve with complex multiplication and so on, work of Zhao and work of, I think Raza's work also comes in, but I'm not very sure. But somehow you can compute the two part of Sha of P of Q in these special cases.
Yeah. So Sujata, I will explain the calculations.
Yeah.
As I know that Ye Tian made it a very untrivial work. Untrivial. I mean, because of course, he extends Zhao's way, but Zhao's way is heavily dependent on this admissible sequence. I mean, this sequence, you need also Zhao added this condition. This is the condition you can roughly understand that the pi I over pi j, the Legendre symbol is chosen. Yeah. For example, if you think this is 1, then that also satisfies this condition for any ij. So this means that then the family of elliptic curve is very limited. But Ye Tian must explain this to any pi 1, pi 2, pi n, I think. But what I don't know is, as if he's still limited on the subgroup, he needed to, his condition is to limit the class number, but that's nearly equal to, not convenient, but the idea is the same. And also what Ye Tian did is, this is Coase and Wiles formula, but they also have a similar formula from the Higler points to calculate the LF prime E1. And then the argument are the same.
Yeah, there are two ingredients in this.
Yeah.
From what I remember, so there's Zhao's work, which is one ingredient in computing the left-hand side.
Yeah.
The other ingredient is this one. You have another explicit formula for, explicit L values and integer points. Right? And Liang, that's my memory of the joint paper that we wrote.
Yeah.
Liang actually wrote a program.
Yes.
Explicitly computing the right-hand side.
Yeah.
So, summing up, you have techniques to compute explicitly the left-hand side in this particular case. You all you need is a computer.
Yeah.
You elliptic curve, and then you spit out the left-hand side. But now you want to check the two part of the Birch and Swinnerton-Dyer conjecture. Remember, theory doesn't tell you anything about the two part. But you would still like to know, I mean, it will tell you, theory will tell you that the two part is also true, but you would have to develop all the reservoir theoretic machinery that we did for the prime t equals 2, which is partly done, but they were not covered in the lectures. In the lectures, we always simplify things. We said t is greater than or equal to 3, greater than or equal to 5 or 7, and so on. So that's what is challenging about computing the two part. So, but luckily for the two part, for the left-hand side, you have these techniques to compute the left-hand side value. And the right-hand side, what is not very clear to me, again, the computer programs can do all the Tamagawa factors, CP of P, P of P function, all that can be done. So the real mystery is Sha of Q. So classically, what people were doing was pretending that Birch Swinnerton-Dyer is true, and then getting a value for SHA of E of Q. Right? If you believe Birch Swinnerton-Dyer, it gives you a value for SHA of Q. Then using other methods, they have actually proved that this is the value of SHA, especially for two parts. If you look at Cremona's tables, all that was known much before Iwasawa-Tate. Like already Birch and Swinnerton-Dyer in the last century itself, they had explicit examples of elliptic curves over Q where the two-part was fully known. Okay? But the missing link here is somehow you can push it further thanks to work of Zhao and Razar, if I'm not mistaken. But I could be wrong.
Yes, I think, you know, what we did, this is an inequality. But yesterday, I think maybe we could follow those way to make a, add some.
The thing is, you can compute the right-hand side as well. Okay. And so then, you see how you have an explicit verification of the Birch and Swinnerton-Dyer conjecture for the two parts, which so far we did not cover in the theoretical aspects. So somehow that's the thrust of this.
Yeah. I will explain some of.
So, like about that formula,
Which one? This part?
No, the M.
The product?
Yeah, but the choice of pi i's, that's the.
You mean the choice of pi I?
I'm just confused as to why the conductor is a band. Gn, so that you get R.
You mean the conductor? Yes. I have to tell you that the truth is the conductor is really is this, and you to calculate the conductor is. I mean, maybe you can read the paper. It's just carefully calculated. It's easy to calculate the conductor.
That's for any algebraic.
Uh-huh.
That's for just some algebraic.
I think it's not difficult to calculate the Gn. Yeah, not difficult. Easy.
That's why you get R.
Yeah. Only this is the untrivial argument. I mean, it gives a lot of two factor. The only problem is that if the two factor in this subgroup is big, then you use this way, the most two factor you can find is 2. Is n. You can't find more. That's the limit of this way. It's heavily dependent on the subgroup, the suffrage group. So I want to explain a little more about the calculations. Yeah, so for any n, this holds. For n equal to 1 or 2 is non-trivial. Yeah, I think Zhong is very powerful in analysis, right, Rujatha? It depends on, take some part of the sum, make it convergence. Yeah. It's, I think you talk about that, Coach and Wiles formula. Did you? No?
We have so far not used, there is no lecture, there has been no lecture on the computational side at all, right?
Okay. Then I will explain some of our calculations. I think I want to leave this. I will cancel this. So the TED software group From the P, as I think it's from the P divisible group, the structure of theta suffix group is equal to this direct sum. This is how to explain? It is, remember the P infinity torsion point group. I mean, it has this structure. And this is equal to this plus a finite group. So if we want to prove that this is finite, then obviously we must have P must be equal to 0 for any P. So what we did for the calculations? So the calculation by Rujatha and me, and maybe okay. I have no. I mean, I didn't know notice the term. Maybe we should put John Coates the first. Is that we calculate this one? We calculate this one for a lot of p's. The main conjecture gives that if REP is greater or equal to GE plus TEP, yeah, this holds. And if REP is equal to GE, then of course we have TEP must equal to 0. And oh, sorry, I didn't explain REP. REP is S, sorry. I'm sorry. Is order to S equal to 1 L E over Q S, maybe algebraic. Is this one? But from the formula, I mean from this formula, this REP is, we can calculate. This is the one we can calculate. By the way, P must be good ordinary. I mean, is good ordinary. In fact, is IEP is not this. Sorry, IEP is not this. Is this, where LEP is LEP is 这个 is a trace, is the trace F minus P of this trace. KEF of K epsilon P omega infinity over F L is just this part making N is equal to P. The point is that you have L1 and LP has some congruent. It's maybe Koch result. They have some congruent conditions. So Calculate this case at n equal to 1 is not easy because it is not convergent. Calculate this is easier. I mean, maybe more p or more some power of p maybe. Anyway, we can have this result. We can have this result. This is from the main conjecture. So the tasks, I think when Zhing give me the tasks is to calculate this part. To calculate this part. This part is you have to use this formula. I mean, so what you have to calculate is p omega infinity divided by f L. I mean, you want to calculate this. In fact, what we want to calculate is a minimal polynomial of this element over Q. It's the x coordinate of f torsion point. F torsion point. So in fact, what you have to do is to calculate the the minimal polynomial of f torsion point, and then calculate all this. So what we calculate is for this E1, E2, E3. We calculate 6 elliptic curve, in fact. E4 is y square equal to this. I must and P is smaller than 30,000 and P congruent to 1 mod 4. Then we always has the P part of the theta soft group is 1. And in fact, I calculate some more elliptic curves over Q over this field. I calculate the sum, but there's a long time and I forgot which curve I calculated. But I also calculated about 10 elliptic curves, in fact. Not only over this field, over this field, and over some other field. Later, when Rujatha went to Beijing, I explained the new formula. Yeah, this is my new formula. If we write still the E is y squared equal to x cubed minus dx, and the same symbol, then L Gn per psi Mn 1 over omega Mn is equal to 1 over 2 Gn of the trace Rn over K of the Y Cn omega n over G over X Cn omega n over G. Oh, okay, sorry. My n is equal to Mn. The same with the admission. So this trace is much easier because the minimal polynomial of this one is much more simple than the minimal polynomial for this. And of course, there is another difficulty to calculate this is that if n is odd, then this is a polynomial in PZL, then times P prime ZL. This one is, P prime, this is a y coordinate. The y coordinate is, if you take the primitive F torsion point, the y coordinate is, the P prime is in K joint with P. This is easy to prove. This is easy to prove. But you have to calculate the explicit expressions. It's very hard. But if you use this formula, then you only want to calculate is the minimal polynomial. You don't need to calculate. That is very hard to calculate. So this is, I think this is a good improvement. So later, I think, use this, we can easily to calculate to this. I did this, but I never write it down, but I checked that this is right. Also, there is some, there exists some P such that sometimes REP is equal to GE plus 1. At this time, what you can prove is that the theta suffrage group is finite. But then you can use the periodic analog of BSD conjecture. In fact, I use Christian Woolrich's way to check that for this, we say the exceptional primes. Exceptional primes, they also have this. But of course, we also prove some theoretical results for the growth of TEP. But for the calculation part, what we can prove the best, I think, is this. Yeah. And I guess that it's still the fastest to check the P part of theta suffrage group. Because this program is much faster than Woolrich's method. Because Woolrich, if you take, for example, P equal to 1997, if you use Woolrich's way to calculate the P part of theta suffrage group, it's I guess that we can't get the result before we die. But we use this way to calculate this, then just after several seconds, then the result comes. I don't know if I saved the program in somewhere, but several years ago I showed to a lot of people how fast it is. You just type and then the result comes out. So I think maybe now what I want to do is to find the application of this formula. Find a theoretical application. But now I don't find a good application. My point is, if we can find some more two factors from this formula. These two factors grows from the you consider the Galois group over, you used all of the Galois element of this. The two factors, in fact, they grow from the Galois group. So you used all this Galois element. What I want to do is, if we find some special Galois group in this formula, to find more two factors. Because you can also use this way to do this, use this formula to do this. This is also okay. I showed it to Rujatha, but Now what I'm really confused is it's hard to get one more two factors. So that's a problem. I think my talk stops here. Thank you.